So welcome. My name's Alan Smith, and I'm going to talk about large language models demystified, a bit about the maths behind the magic of the GPT language models. A bit about myself. I've kind of resisted the temptation to go into architecture or project management or sales or anything. I like writing code, so I've just focused on writing code since 1995 when I started my career. I'm at Microsoft AI, Microsoft MVP for artificial intelligence. I've held the title since 2005 in various disciplines, and I do a lot with the community. I've been involved in organizing conferences and helping with coder dojos, and during COVID, I was doing quite a bit of stuff on YouTube. I was scheduled to talk about GPT versus StarCraft. Unfortunately, the random nature of these language models meant that as soon as I stood on a podium in front of people, the demos didn't work as good as they did back home. So I do have all of that stuff on my YouTube channel if you do want to go and check out that stuff. I've edited out when things go wrong on those YouTube videos. First of all, I'd just like to thank the other YouTubers and community people who've done a fantastic job of being able to help me to learn how these language models work. Some of you probably have seen some of those at those channels there. I'd especially recommend 3 Blue 1 Brown has just done a couple of series looking at the maths behind transformer models, which is fantastic to watch. I really recommend that. So GPT. We come in and we ask it a question. We ask it how to make cheese, and it spews out all of this actual response of how it can make cheese. And we sometimes think it's human. We sometimes feel sorry for it. We sometimes get angry when it makes mistakes. But really, it's just maths that's going on behind the scenes. So hopefully, I'll be able to explain a bit about how that maths works. The only thing these models do, the GPT models and many of the large language models, is given a sequence of tokens, the model will predict the probabilities of each token being the next token in the sequence. That's it. That's the only thing that they do. And we put a lot of code and stuff going around to kind of make that work. There are some seats at the front and scattered around there if you're looking for a seat. So we say the cat sat in there. And GPT basically comes out with these various predictions that floor is going to be the most probable token with 7.64%. So we stick that on the end. We send that sequence through GPT again, and it comes out with comma, 26.14%. So we stick a comma on, send that through again, and it comes out with and we slap that on the end. That's why we kind of see this stream of words or tokens appearing as GPT is making its predictions. Sequence prediction, they can be variable length. So we can have different length. The cat sat on there. The king of rock and roll is Elvis something. Or, load the training data.txt into a list and display the top 10 lines. And it will produce some Python code to do that for us. The order is also important. If we say the film was not bad, in fact, it was very good, compared with the film was not good, in fact, it was very bad, we've just swapped the entire sentiment of that text by swapping the position of 2 words. So position and order are very important. Also, long-term dependencies. The cat sat on the floor. It had just been cleaned, so it is going to refer to the floor. Versus the cat sat on the floor, it had just been fed, where it is going to refer to the cat. So the language models do need to understand what these actual words are, and this takes place in the attention mechanism, which goes on inside these transformer models. We also get prompt engineering to make things better with the actual question answer. So we're telling it what to do, we're telling it what not to do, and then we're supplying it with a user question. And all the model is doing is predicting what tokens are going to come next in this sequence, one at a time, based on that tokens. We can also do retrieval augmented generation, where we basically slap some information in there, typically from a search engine. But again, it's just predicting the tokens, what is going to come next in that sequence. And then also we've got chat history. So we ask it, what is the capital of the Netherlands? There is no state in these models. So every time we're going to be asking it a question, we're sending in the entire chat history of that chat so it can actually understand what's going on. And you hear about these models being able to take 4,000 tokens or 16,000 tokens, and that refers to how much history and how much data we can put in when we're using these retrieval augmented generation options there. I'm working with GPT-2. Jodie's session this morning was fantastic. So if you're in there, she did mention a bit about GPT-2. The reason I'm working on it is I can actually run it on a computer that I can carry around in my backpack, which is not the case with the other language models. Also, it's open source, so I can download the source code, I can stick breakpoints in, and I can go and see how things work. So if I set this thing as the startup file, and then Control F5. Oh no, why is my screen gone?
I'm ChatGPT 2, a friendly chatbot. How can I help you?
I'm going to stop that. Is it when I... okay, I'll try that. Duplicate. Yes. It takes a while to load the model.
I'm ChatGPT 2, a friendly chatbot. How can I help you?
What is the capital of the Netherlands?
Dutch capital is Amsterdam.
Is it nice there?
It's nice there.
What can you do in Amsterdam?
You can do anything in Amsterdam.
Yeah. So you can, it's true. Yeah, so you see that this is when data scientists got really excited about this technology and thought, wow, it can actually generate text. And it's syntactically correct, as Jody was saying this morning, but the general public wouldn't really get excited if this was a chatbot available. You know, it's like having a conversation with a 4-year-old. It's going to come up with crazy answers. But the data scientists realized that if we just throw data at it and throw parameters and throw lots and lots of GPUs at it, we're going to get something that's going to perform a lot better. So yeah, another quick demo on the sequence prediction. If I just set this guy as the startup file, we'll see some other examples of how it's actually making that sequence prediction and the statistics behind that. So what I'm doing is I'm basically running some code. Actually, I'll demo it in my notebook. I think it's this can basically show how this works. So what I'm doing here is importing some libraries. So I'm importing the PyTorch stuff and then transformers. I'm importing GPT tokenizer and GPT LM head model. These are from Hugging Face, and then I've got PyPlot so I can draw some graphs. We then create a tokenizer and load up the model. Which is this code here. I haven't got a big GPU on this laptop, so I can't stick it on the GPU, but that code would normally do that. I'm then defining some text strings that I can actually feed through the model and printing them out. And now we can use the model to predict the next token in the actual sequence of tokens. Remember, it's tokens, not words. So I'll go for text 0, actually. The cat sat on there, and run that. And then what we're getting out is this actual tensor, which is 1 by 5 by 50,257. And to make sense of that, what we can do is actually do a softmax operation on it and get the actual probabilities out. So the cat sat on there. It's got floor with 7.64%. There's other things that we can do as well. So if we say the king of rock and roll, I'll switch to this demo because this kind of highlights and uses pie charts. So if I just do Control F5, we'll start without debugging. Again, it takes a few seconds to load the model. And actually, no, it wasn't that one. It was this one. Sorry. Let's start without debugging. What this is going to do is to take a few sequences of text, convert them into tokens, send them into the GPT model, and then show us the actual probability distribution. So we've got the cat sat on there, and we've got all of these various distributions there. It has the probability of all of the 50,200 or so tokens. So imagine that this is one of these wheels at the fairground, where you've got, you know, the grand prize is this kind of small wedge. And when you spin the wheel, assuming the wheel is not weighted, it's going to land on one of those things. So it's kind of like one of those probability things if this pie chart was a wheel. Yeah, I did this in Helsinki last week. So it's saying Helsinki is the capital of Finland with 42.76%. Estonia and Russia are down here, which is a little worrying. And then it does predict how to do C#. So using system dot, it's got other stuff there. And then If you're a Python programmer, you typically import NumPy as NP, and it's making that correct prediction there. And then the king of rock and roll is Elvis. Well, Prez. These are tokens, remember, not words, and Presley is not a token, so Prez. Also, this is prefixed by space as well, because these typically are. And then we've got Elvis Costello here with 2.76%, because maybe it's going to be that. And then if we say the king of rock and roll is Elvis Prez, very high probability that the next token is going to be Lee. So it's really dependent on the kind of a probability likely distribution. If you say my favorite animal is there's all kinds of variation in there, and it's really just predicting what it thinks the probabilities of these next tokens are going to be. So let's drop back to the slides. So we're sending in a question into this language model. We can see the architecture there. However, neural networks don't really do text. So we've got to think about how we can get the text into a sequence of numbers. And this is done but through the process of tokenization. So this text is coming from the tokenization site that we've got at OpenAI. I really like this bit of text. It's been replaced by another bit of text on the website. But the thing I like about this is the three things here that are really important. Tokens are common sequences of characters found in text. So this tokenization process is separate to the language training model. They take the actual training data set and they do some maths on it, and they figure out, right, we're going to have a vocabulary of about 50,000 tokens. What is the most efficient way of representing this text in 50,000 combinations of characters? Now, the majority of the training data is in English. So the tokenization is much more efficient with English. The models understand the statistical relationships between these tokens. I would argue that the language models do not understand text. They just understand the statistical relationships between the tokens, and they predict the next tokens. The tokens could represent musical notes, and in which case it will predict the next musical note in a sequence. All it's doing is maths with the probability distributions of tokens. We've seen in the code that we convert the model into tokens and we just send integers into the models. We don't send text into the models. So I would argue that the models don't actually understand text. But what they're really, really good at is producing the next token in a sequence of tokens. I slightly disagree with that because they don't actually produce the next token. They predict the probability distribution of all of the 50,000 tokens. And we may or may not want to choose the most probable one, depending on how creative we want the text to be. A good example here of why it doesn't understand text and why it can get confused. Give me a well-known song lyric with the word wind, as in wind a watch. And it came out with Blowing in the Wind by Bob Dylan. I said, I wanted, wind as in wind a watch, not blowing in the wind. Sorry, I misunderstood you. And it came up with Against the Wind by Bob Seger. And this one's really, really interesting. Listen to the wind blow, watch the sun rise. It's got wind and watch in it, but it's the wrong wind and it's the wrong watch. And here we can see the confusion in that it's kind of treating these as tokens rather than words. The token for wind or the token ID for wind and for watch are the same. It's the same, even though they're different words, it's the same sequence of letters, it's the same token, and it confuses the language model. So tokenization, it's more efficient in English. If we take English, that comes out to 45 tokens. You can see the word "the" is represented differently. Also, as I mentioned, all of these are prefixed by space. If we use space as a token, there will be about twice as many tokens. So it makes sense to include the space when it's a token is the start of the word. So most of these, in fact, all of these, the actual English words are tokens. If we go to, we're all programmers in the audience. What's the significance of 11 and 13 and comma and full stop? ASCII, yeah. The first 256 tokens are ASCII characters. So that basically allows us to, represent any text there. And you'll see these ASCII characters popping up there. If we take Swedish, it ends up getting more fragmented because there's not that much Swedish data in the training data. So here it comes out to 83 tokens. If we take Dutch, we've got 71 tokens. Finnish, as in Finland last week. That's kind of from the European languages, the most inefficient one that I've found. And then we've got Telugu, which comes out at 622 tokens, even though there's only 247 characters there. Now, this is showing kind of the efficiency of the tokenization using different languages, and this is showing the language understanding of a GPT-4 compared with GPT-3 using the MMLU, which is one of the stats that Jody talked about, one of the actual language tests for kind of analysing how accurate these languages are. We see that GPT-4 is much better in English than it is with other languages. However, GPT-4 is with other languages is usually much better than GPT 3.5 with English. So that's kind of the actual stats there. It's kind of a rough correlation if you plot this one against this one. Really, there's some kind of correlation between the tokenization efficiency and the language understanding, but it's not really a straight line. You can see Telugu's at the bottom there, and also there Telugu's the most inefficient of these languages listed for processing tokens. So one of the things I've heard is that English is the new programming language. I'm not saying that just because I'm from England and I speak English. You should aim and endeavour to write your prompts in English. Several reasons for that. GPT models are most accurate with English because they've had the most amount of training data in English. And you can see on the accuracy charts they're more accurate. Billing is based on the number of tokens. So if you're using Swedish or Finnish or Telugu, it's going to be more expensive to send the same amount of kind of meaning through the language models. Throughput is based on number of tokens per second, so it's going to be faster processing English. And also you get these quotas based on how many tokens you can use, and also the models have a maximum number of input tokens. We're developers. If we can make something run, say, 20 or 30% faster and 20 or 30% more accurate, and it's going to reduce the cost by 20 or 30%, we'll do that. So even if your model is a RAG solution that's dealing with, text in your native language, it's generating outputs in your native language, the questions, users are answering questions in your native language, writing the prompt in English still works. You can still do that. And I would recommend doing that. Just for a test, I asked it how to make cheese in Telugu, and it came out with an answer, which was this thing here, recommending using cheese powder as the main ingredient. And then it gave up. It switched back to English, offered to generate a poem or a story. And then it got really weird and generated an image of the frozen characters in an autumn-bound enchanted land that you requested. I asked it how to make cheese, but there is obviously some confusion and understanding. Now, that's an extreme example. I've done loads of testing, and that was just the one that came out as being really, really crazy. But you can see that there is kind of a correlation in between the language understanding and the actual quality of the answers that you're going to be getting. However, neural networks don't do integers. They do floating point numbers. So what we've got to do is another stage of conversion and get these tokens into floating point numbers so we can actually start to do maths with them. And this is known as embedding or vectorization. And again, Jody was mentioning about this, how we can vectorize text or do text embedding to get the sentiment of text. So we take the word cheese, and in GPT-2, I think there's 768 floating point numbers that basically have this embedding or vectorization of the word cheese. Now, humans can't think in 768 dimensions. We can, just about handle 3 dimensions. And we're developers, so we've built web pages and we understand about, red, green, and blue color, how we've got this kind of vector where Azor is 0, 1, 2, 7, 2, 5, 5. And data scientists always work floating point numbers between 0 and 1, so that's 0. 0.5, 1.0. And what we can do then is take loads of colors and we can stick them into a 3D space, and we can see that similar colors are basically close to each other in that 3D space. And measuring the distance, 2 ways of doing this. We can either use the is it Euclidean distance or something, the actual distance that we measure between those 2 points, or we can use cosine similarity. And cosine similarity will basically say if they are kind of along the same angle. So dark Azor would be somewhere around about here somewhere. And because of the actual angle, the ratio of those colors, you'd say all of the colors along this line are similar, and they have the same cosine similarity there. We can also do this with words. So word to vec basically has this database here, and this is the embeddings projector, and there's 10,000 words in here. Each one of these is represented with 200 dimensions rather than 768. But what we can do is we can do this nearest neighbor search, and we can take those 200 dimensions and we can squash them into 3 dimensions so the human brain can understand them. And then we should see that similar words are together in similar locations. I need to get a faster laptop, but eventually it will get there. We should be able to see this. So this word-to-vec database, as Jody mentioned, it was part of the actual, timeline of research that people were doing when they were looking at natural language processing. Okay, so now we've got this kind of a cluster of words, and we should see that words that are similar are going to be in the same place. So let's go over here. We've got a few. Oh, these seem to be relating to classical music. And we've got some over here. Diseases, AIDS, that's kind of medical stuff over here. We've got like Greek letters over here as well. 50, 70, tens, millions, hundreds, and all of these are numbers. So this kind of a cloud and using this kind of vectorization is a way of finding out sentiment and what words are similar to others, because the language models want to understand that good and great and fantastic are words that kind of have some kind of a similar sentiment or similar meaning. So we'll start to look at the actual transformer architecture and see kind of what goes on in these language models and how the attention model actually works and how these calculations are going to actually get some answers. Now, this is from the white paper, Attention is All You Need. And the white paper is really written about doing translations. And Jody mentioned this morning, that instead of just doing translations, what we're really using GPT for, this transformer architecture, is for sequence prediction. So what we can do is we can just basically, forget about this bit and just focus on the decoder and look at how we can take our data, we can send it in, and we can get the embedding and the positional encoding. Because remember, position is important as well as the actual words, and then we can actually kind of follow through how that goes through the network. So focusing on that bit, we see how the tokenization works. The cat sat on there is going to be lookups in the tokenization vocabulary to get the integer numbers that are going to be those token IDs. What we can then do is perform the embedding. Now, during the model training process, we create something that's known as an embeddings table. And this will be present within the model. And the dimensions of that embedding table is 768, because each token is going to have 768 floating point numbers that describe it in that 768 dimensional space. And then we've got the size of the token vocabulary, which is 50,256. And what we do is we just basically do a lookup. So we look up number 464, 3797, 3332, 319, and 262. And what that's going to give us is the actual embedding vectors for those 5 tokens. And that's what's going to be fed in the model. That's the actual embedding vectors, which is going to be basically the number of tokens by 768. So that's going to give us our embedding vectors. The next thing we're going to get is the positional vectors. And there's also a positional lookup table. And what we feed into the positional lookup table is the actual position of the token. So this will basically be 0, 1, 2, 3, 4. And we perform those lookups. Now, the positional vectors are going to give some kind of a meaning of the position. They're still going to be, 768 dimensions, but they're created not from the actual training data, but using sines and cosines and actual values. So it gives some kind of indication that this position is going to be relevant to this particular token. So we have the positioning information. And then what we do is we add these two together. And that's going to give us the encoder input values that we're going to be feeding into the actual model. So, as I mentioned, the cool thing about having the source code available is I can stick breakpoints on. So if I go to this next token prediction, I've got this set up as a startup file. I'm just going to change the input text to this and do Control F5. No, I'm not going to do Control F5. I want breakpoints. So I'm going to do F5. And what this is going to do is to load the model in memory. If I press enter, instead of having to type in the text, it will say the cat sat on there. But we're going to be hitting breakpoints. And if I go into the watch window, I'm using Python here. So this self will tell me, what class I'm in. So we're in the GPT-2 model. We're in the constructor of the GPT-2 model. And then I can run to the next breakpoint. It's asking me to enter some text. I'll just press enter. And now we're in the GP2 head model. And we've got our input IDs. So these are the actual token IDs that are being passed into the model. If we look in here, we can see that the tokenizer is actually separate from the model itself. So we're doing tokenizer in code, we're passing in the text, we get the input IDs, then they go into the model, and we get to, where is it, the breakpoint that I had when we're here within the model. We've got those tokens. So if I do an F5, you can see now that we've got the position IDs, 0, 1, 2, 3, 4, for the actual tokens. So what we're doing is we're actually getting the embeddings. So when I said there was an embeddings table in the actual model, it's this WTE, which is the embeddings table. So what we do is we feed in these IDs, and that's going to give us, if I just step over these 2 lines of code, the input embeddings here. And if you look at the size of the input embeddings, you can see that this is 1 by 5 by 768. Now, pretty much all neural networks, we can train them using batches in the actual training process. So the 1 basically means that we're just sending in 1 actual sequence. When we're doing inference, when we're actually doing this, we're usually just sending in 1 stream of text, but the model does support sending in more if we want to do that. So that's pretty much always going to be 1. Then there's 5 tokens, 768 dimensions, and that's our actual embeddings. We do the same thing with the positional embeddings. So if I just step over that, you can see now that we've got our position embeddings. That again is 1 by 5 by 768. And then we're going to calculate the encoder input values, which is hidden states, which is just adding the input embeddings to the position embeddings. So I can step over that code there. And what we've done there is just this calculation that I had on the slide deck there. So the next thing we're going to do is to look at what happens after that, how it does the actual attention calculation. And this is the actual formula for that. It has the query, the key, and the value. And these are going to be kind of calculated or extracted by using floating points in a layer in the network that's basically trained to be able to do that. And we're then performing this softmax operation on this matrix algebra. So there's a lot of matrix calculations. The good thing about the gaming industry and loads of kids playing games, or adults playing games as well, and spending ludicrous money on big gaming GPUs, is that the same GPUs are really, the same calculations in 3D games are pretty much similar to what we're doing when we're training these models using matrix algebra. And this is basically what's driven the rise in these models. NVIDIA is now, I think, is it the most valuable company in the world still? There's a news story on that they'd overtaken Microsoft because they're basically making these GPUs. So what we do now is we take the encoder input values, that's 1 by 5 by 768. We use a convolution layer, which is going to generate different representations of the input value vectors for the attention mechanism. So this is going to come out with this 1 by 5 by 2304. And we're then going to split that into these kind of 3 sections. And this is known as the query, the key, and the value. I'll explain a bit more about those later on. Now, it's a multi-headed attention, and in GPT-2, we have 12 attention heads in each layer, and we have 12 layers. So that 1 by 5 by 768 is going to be split based on the number of heads, and that is going to go to 1 by 12 by 5 by 64. And what it's doing is it's splitting the dimension of 768 between 12, and that's giving kind of 12 instances of 64 there. So there's one batch, 12 attention heads, 5 tokens, and 64 floating point numbers in each attention for the query, the key, and the actual value. So the query, the key, and the value are used to get the attention, which is how the words relate to each other. So I don't normally speak at these types of conferences. I'm normally at Azure conferences and .NET conferences. So I can be the query. I came here, and then each of you in the room is going to be the key, and then the value is kind of what connection the key has to the query. So what we're doing is we're looking at all of the words in the input tokens, or all of the actual tokens in the sequence, and saying, well, how does this word relate to that particular word here? And performing calculations to try and figure out the actual sentiment. Remember, these vectors that we've got for the words, they kind of describe the sentiment of the words. Similar words are closer together in the actual vector space. So what it's going to do is to be able to figure out that if it's the cat sat on the floor, it had just been cleaned, that it is going to have a connection to the cat. So what we're doing is within this matrix operation, we're taking the query, we're transposing the key, multiplying it by that, dividing it by the root of 64, which is the number that we've got here. That's just something that they've figured out works better for the actual maths there. And then we're performing this softmax operation. I'll explain a bit more about softmax later on, but if you've played around with PyTorch or TensorFlow, you probably know what softmax does. In there, it gives us a probability distribution from a sequence of floating point numbers, and it's important when we're doing the calculation of the temperature. So what this is going to give us is the actual attention when we've done all of this maths. Now, the vectorization or the embedding gives us the meaning. The positional vectors and positional lookup gives us the position. But what the attention mechanism is doing is calculating how words relate to other words and what the connections are and long-term dependencies between all of the other words. And it's that's really doing the magic that's allowing these models to make predictions. So if I drop back to the code, we should see that maths taking place in here. So what we've got is we've got the hidden states. Now the hidden states was that, I think we got the shape on that. That was that 1 by 5 by 768. That was a result from adding the position vectors and the embedding vectors for the tokens. And then what we're going to do is the maths that I had on the actual screen, where we're taking the attention, we're putting in the attention, and then we're splitting that by the actual dimensions. And what that's going to give us, if I step over that, is going to give us the keys, the queries, and the values. But here, the keys, the queries, and the values are for all 12 of these. So if we look at the key shape, we can see that's 1 by 5 by 768. We then split it based on the number of heads, and there's basically 12 heads in this particular model. So if I step over that, then we've actually got the key, the query, and the value being those dimensions of 1 by 12 by 768. And that's what's going to work as we run through that particular network. Now, because there's 12 layers in the network, we're basically going to do this 12 times before we actually get to the results. And the main difference between GPT-2 and 3 and 4 is they've just got more layers, they've got more parameters, they've got more attention heads in there. They're just bigger and larger. And eventually, we're going to get the actual output that we can start processing and making sense with. So if I drop back to the slides. This is just explaining about what happens, because here the word it is ambiguous. We say it had just been cleaned. Well, is it the cat that had just been cleaned or the floor that had just been cleaned? And what the attention mechanism is doing is it's taking the word it, and we've got, the differences between these two words. And if we focus on it had just been cleaned, then it has more of a connection with floor and more of a connection with cleaned, because floor has more of a connection with cleaned. And it just basically shifts the vectors in that high dimensional space so that it is going to refer to the floor, and it understands how those actual words relate to each other. So the model will basically look like this. We've got basically 12 heads, and we've got a couple of other layers to do the normalization and the feed forward and so on. And then this is just going to repeat 12 times in the GPT-2 model to give us those actual predictions. So that's it. We can predict the next token. Fantastic. So this means that we can actually start generating text. So let's just see what that does. When I go back to the next token prediction, and I'm going to take this and just do the king of rock and roll is Elvis, something that's easy to predict, and I'll do Control F5. We don't want to be hitting all of these at these breakpoints. So I'll just press enter. The king of rock and roll is Elvis, and we've got Prez coming up there with 64.98, so let's bang that on. And then Lee, 99.76%. Then we've got full stop. Yeah, he's a rock star. And he's a rock star. He's a rock star. So if you go to a party and you just say the most predictable thing every time, all of the time, you're going to be really boring. Nobody's going to talk to you. And this is what we're seeing here, that there's more to text generation than just predicting the next bit of text. There's all of these other things here that we may want to predict. So we can take he and then was. We can drop on 3 and then a couple of other tokens. And then I'm just going to drop some random things in. And as we put a bit of stochasticity or randomness or variation into these prompts, then it's actually going to start to generate stuff that is more interesting than he's a rock star and he's a rock star and he's a rock star and he's a rock star. So there's a couple of parameters that are really important when we're working with these models. One of them, people kind of understand sort of when to use it, and that's temperature. So temperature, normally we say temperature varies between 0 and 1, and this affects the randomness or the creativity of the network, and using values like 0 is going to be very predictable and 1 is going to be very unpredictable. However, it goes up to 2. Normally, when we're working in a portal, you're working in the Azure OpenAI Studio, the slider only goes up to 1 because things get very predictable if you go above 1 when you're using GPT-3. If you go up to 2, it can just start generating garbage because it kind of picks one of these random ones. So temperature, it does have an effect on what is going to be generated. And what I didn't mention when I was running through my little demo here is that we've got the cat sat on that. Yeah, so these are my text. Which one are we using? We're using 0, the cat sat on there. And it's coming out with this actual probability distribution here. So the cat sat on the floor at 7.64%. Now, we've got the formula for temperature here, because what I'm doing is I'm getting the next token logits, and this is kind of a series of floating point numbers that is not the probability distribution. They're just like floating point values, and they're going to be higher for more probable tokens and lower for less probable tokens. And what we do is we divide this by the temperature, and then we perform this softmax operation. And what softmax will do is basically take all of those numbers and do some maths on them so that they basically add up to 1. I think I've got the formula for softmax on my slide somewhere. So what it's doing is this. There's some logarithms involved, so it's non-linear. But it's just really taking a series of floating point numbers and converting them into an actual probability distribution. So if temperature is 1, then it just divides them by 1 and we just take their regular values. However, what happens if temperature is 0? Bad things happen because this is a divide by 0 operation. So in this implementation here, I can just drop temperature as being something very low. And you can see here that floor now has a 100% probability when we're using a low temperature. If I drop the temperature to 0.5, you can see that floor has 24% probability. So what it's doing is it's kind of shifting the probability distribution. If I go above 1 and drop a temperature of 2, you can see that all of these top 10 have quite a low probability, and it's making it more probable that other tokens are going to be the ones that are chosen. So to make this a bit more visual, I'll cover top P first and then I'll show you the actual animation. So that's kind of what temperature does. Top P basically puts a hard cutoff on the tokens being chosen. So if I choose a top P of being 0.1, it can only choose floor or bed, and it's most likely to choose floor. That is a 0%. There's no way that it can choose couch or ground or anything else. And the top P is basically varying how much of that actual slice we can make the actual choice from. And I think when we're developing these applications, it's good to understand what temperature does and what top P does and how you can kind of combine those various options. Because I've seen people standing on stage talking about large language models, and they don't really kind of have an understanding of what top P does and how it works. So I basically created these animations because I was really curious about, well, how does the probability distribution affect? So we're sending in the cat sat on the, and we've got the temperature here starting at 1 and the top P, and I'm using the same values for temperature and top P, and we can see how the actual probability distributions are changing there. And it starts to get more interesting as we get to the lower values here, because what we see is that with top P, these things start actually disappearing out of the actual probability distribution. So all of the earlier ones have gone now. They can never be chosen. Here, they can be chosen, but there's quite a low probability of them being chosen. Now, if we go back to the temperature of 1 and top P of 1, we don't put any restriction on. So there is a tiny chance that it's going to land on here and it's going to say the cat sat on the cheese, or the cat sat on something that was completely inappropriate. So we can see in the slide I was mentioning that in the portal, they're specifying a top P as 0.095. And that's just basically chopping out the 5% of the tokens that we probably don't want to choose. And then we're actually varying the actual temperature there. And in the guidelines, it says vary the temperature or the top P, but don't do both. So what this is doing is we can vary the temperature, but it's never going to produce anything really unpredictable, even with a temperature of 1.0, because top P is going to be filtering off that. And then as we drop back to the animation, as I go towards this end of the probability distribution, you can see that they disappear. And when we get round about here, you can see we can only have floor and bed with a top P of 0.135, but with the temperature, we've got floor, bed, couch, ground, and all of the others. All of them do have a probability distribution, but most of them are really, really small. So to see how temperature has an effect on things, what I can do is drop back to the, I've got a demo called temperature theory. I think it's this one here. Set this one as a startup file and do a Control F5. So what this is going to do is to cycle through different temperatures and create different outputs. I think I actually want to drop in I think I got rid of the input on that. So let's just set this one as a startup file. No, it wasn't that one. It was the temperature theory. Yeah, I'll just comment that back in. I always do this demo at the end of the session because I've been doing this and the audience falls about laughing and is in stitches, and I have no idea why. Because it's random in nature, or stochastic as data scientists would have us say, it can generate some unpredictable results. Maybe it generates inappropriate results. So I apologize in advance that it does that. So with a temperature of 0, this is GPT-2, remember. It's just saying it's a very good dog, it's a very good dog, it's a very good dog. The favorite animal is always a dog because that is the most probable token. However, as we start increasing it, you can see that it is making different predictions. It's mostly picking dog, but it will occasionally pick black bear. And then as we increase this, it's got rat, rabbit, cat, rabbit, rabbit, no dogs with a temperature of 0.04. And then it tends to get more creative as we increase the temperature. So I definitely recommend when you're building GPT solutions of varying the temperature. Is there any way you can automate these tests as well? Because focusing on building these kind of RAG-based solutions, you don't just want to have one question and focusing on, well, if I set the temperature as 0.6, then this particular question gets a good answer. It's going to affect all the questions that you send through it. So next session I'm going to be doing at conferences next time round is going to be looking at how we can do testing and analysis of these models, and and be able to analyze how well prompts and how well temperature is working, because we can't just do testing when an answer comes out it's green, and if a bad answer comes out it's red. We need to think about stats and things like that. So as we're changing and modifying the temperature, you can see that this is getting more creative with the actual language that it is creating here. Remember, this is a GPT-2 that we're using, so the answers are going to be slightly less predictable than normal. Okay, let's just drop back to the slides. As well as the temperature, there's other parameters that we can use to influence the actual output. So temperature and top P are the main ones that kind of govern what is going to be coming out of the model. N is how many track completion choices to generate for each input message. So what I've shown is just how we're doing the actual prediction of the next token. Now, what goes on to make the answers kind of nicer and more human readable is it also works with something called a beam search, where it kind of looks, the cat sat on the floor, and if we choose floor, we can choose these 4 or 5 other tokens. If we choose one of those, then we can choose these other tokens. And this is looking at can we generate multiple completions for each message when we're generating those messages there. We've also got a stop sequence. When is it going to stop talking? So when it's generating, I'm doing a question and answer, we could say, well, when a full stop appears, let's stop the actual output. So you can specify, various sequences where it will stop and not generate any other tokens. We can also specify the maximum number of tokens to generate in the chat completion. We may not want to generate really long answers. We may want to generate short answers. Also, we're paying for all of these tokens and it takes time to generate tokens. So that can be specified. There's a presence penalty and a frequency penalty. So if you want it to not say he's a rock star, he's a rock star, he's a rock star, he's a rock star, that's going to be relating to the frequency penalty. We don't want it to keep repeating various things. Now, if you're generating a kid's story or a poem or lyrics for a song, then maybe repetition is good, because you want to be repeating the same kind of phrases or the same kind of words or stanzas within the lyrics of a song in the chorus, for example. But in other more scientific texts, you maybe don't want to do that actual repetition and so on. Also, with generating code, there's a lot of repetition when we actually write code. We don't want the codes to not use the same sequences that we use 3 lines above, because that's going to result in everything getting really chaotic. Also, we can modify the likelihood of specific tokens appearing in the completion. We can also put in a block list and stop certain tokens from appearing in that sequence. So that's all I was going to say. Again, I would really like to thank the other people within the community who've put lots of energy into understanding and explaining how these models work. And again, I would highly like to recommend checking out 3 Blue, 1 Brown's 2 videos that he's done on transformers. They are, I think they're marked as being chapter 5 and chapter 6 in the deep learning series, but don't bother. You don't have to watch the first ones to understand that. And that kind of builds on what I've been talking about and uses animations to show how all of these transformer models are working. So I think we've got about 2 or 3 minutes for questions. So I was wondering if you got any in. We can take questions from the app or from the audience.